So when we look at an entry in the periodic table for a element, we'll see that there's a little box for every element. It has the atom symbol in the middle. The symbol always begins with an uppercase character, and if there is a second character, then that character is always lowercase. And then it'll have a number above it, which we've already indicated is the atomic number, Z, and that's equal to the number of protons, which is the same as the number of electrons. Now, underneath the entry in the periodic table, there's a number that normally has 2 digits after the decimal point, and for helium that is 4.00. Now, I mentioned before that this is not the mass number. It's not the mass number. So the question becomes, what the heck is it? Well, it's often referred to as the atomic weight. And in this video, I'm going to explain what it is and how we calculate it. So, chemists needed some convenient mass units to weigh things that were very, very small. And they settled on this unit called the atomic mass unit. And I've already mentioned it when I was talking about protons, neutrons, and electrons. And how they came up with this scale was to assign a mass of exactly 12 atomic mass units, normally abbreviated as AMU, to a carbon-12 atom. So that's the atom that has 12 particles in total in the nucleus, and 6 of them are protons. So then what we do is we establish a relative atomic mass scale where we just say that 1 AMU is exactly 1/12 the mass of a carbon-12 atom, and then every atom's mass can be expressed, or every isotope's mass can be expressed as either a multiple or a fraction of this number. So when you look at the periodic table, as I mentioned, you'll see average atomic masses written underneath every element, which take into account all of the isotopes that are present in a natural sample of that element. So elements are present in nature in characteristic proportions of their isotopes. So for example, in a natural sample of boron, there are found to be 2 isotopes, one that has 10 particles in the nucleus and the other that has 11. Now, the mass number is going to be near the mass of the isotope in AMU. So a boron 10 atom has a mass of about 10 AMU, and a boron 11 isotope has a mass of about 11 AMU. Now, what's cool is that in any natural sample of boron, the proportions of the 2 isotopes are effectively constant. They're almost constant. And it's found that you get about 19.9% of the lighter isotope and about 80.1% of the heavier isotope. So we got one isotope that's about 10 in mass, and we've got one isotope that's about 11 in mass, and about 80% of it is found to be the heavier one. So on average, if you just picked out, a couple of 100 atoms of boron from a natural sample and averaged the mass, you would expect to get a number that is a lot closer to 11 than it is to 10, right? So maybe you'd get something like 10.8. Well, we can't just kind of draw number lines and sort of eyeball what we would expect the average mass to be. So what we do is we calculate the weighted average. And so I'm going to revise how to do that. To get the weighted average, or the average atomic mass, what you do is you take the mass of the isotope and you multiply it by the fraction of the isotope, and for every isotope that is present, you add that together. So in this case, we've got 2 isotopes. So what I'm going to say is you're going to sum that together for every isotope. All right. So in this case, we've got 2 isotopes. So we take the mass of the first one, multiply it by the fraction, which is simply the percentage divided by 100. Okay. And then you do that for every other isotopes. We've got the second one plus the mass of the second one multiplied by its fraction, which is just the percentage divided by 100. And if we had 5 of these, we'd keep going for all 5 of them. So having done that, what I end up with is the weighted average mass, which agrees with the value in the periodic table. Now, these are sort of like averages across the entire universe. There might be like locations where you find samples that are more enriched in one isotope than the other. So, you know, this is like a universal kind of average. Okay, it could vary slightly by location, and we see that you know, if you look up a sample of a boron that comes from the USA, it might be different from a sample of boron that comes from the moon or something like that. Okay. All right. So we'll do another one. There are 2 naturally occurring isotopes of lithium. One is called lithium-6. It has 6 particles in its nucleus. We would expect it to have a mass of about 6 AMU, and sure enough, it does. The other is heavier. It has 7 particles in its nucleus, and we would expect it to have a mass of about 7 AMU, and sure enough, it does. In this table here, we're given the natural abundance. It's mostly the heavier isotope with a little bit of the lighter isotope. So if I was eyeballing this, I might say, well, it's like more than 90% of the heavier one, that the average is going to come in about like 6.9 AMU. Okay, so let's go ahead and calculate the average. So I've got to take the mass of the first isotope, multiply it by its fraction that's present, so that's just its percentage divided by 100. And then I've got to add to that the same for the second isotope. And I do that, and I'm expecting about 6.9, right? Okay, after hammering away on my calculator, that's pretty much what I got. I ended up with a value of 6.94 AMU. Now, you normally will receive some guidance as to the number of digits that you should include in your answer, okay? So keep that in mind as well, because, you know, you don't want to be bumbling around trying to figure out the significant figures from that. It's normally told to you how many digits you should use. Okay, now those 2 questions that we just went through are probably familiar to you from Chemistry 139. This one here is a new type of problem for you, and I've kind of like typed it all up because it's such a common question that, you know, you might want to like just pause this video and look closely at how I've solved this problem. So it says there are 2 naturally occurring isotopes of silver, silver 107. Unsurprisingly, it has a mass of about 107 AMU, and silver 109, and unsurprisingly, that has a mass of about 109 AMU. So we've got 2 isotopes, right? 107, 109. If the average atomic mass of silver is 107.87 AMU, what is the natural abundance of each isotope? So we aren't being asked to solve for the average atomic mass. We're being given the average atomic mass, and we're told that it's not quite half-way between 107 and 109. It's a little closer to 107, right? So it's 107.87. So if I had to say about the proportions, I would say it would have a tiny little bit more of that one than that one. So maybe it was like, I don't know, 52 of silver 107 and 48% of silver 109, something like that, maybe, right? Like not quite 50-50, tiny little bit more of one than the other. But of course, that's not going to be good enough, right? I'm going to have to calculate this properly. So how do I go about doing it? Well, the problem is I don't have my natural abundances of my 2 isotopes, but what I do know is that if you add together the abundances, if you add together the fractions of all of the different components, just like the mole fractions for a gas, they always add up to 1. So I'm going to use that to help me out here. So what I'm going to say is that the mass of the lighter one has a natural abundance, or a fraction, of x. Then that means that the mass of the natural abundance of the second one has to be 1 minus x, because x plus 1 minus x equals 1, right? So now I've only got one thing to solve for, which is this x. So I'll go through and do that now. So here we go, x being the fraction of the lighter isotope times by its mass, plus 1 minus x, the fraction of the heavier isotope, times by the mass of the heavier isotope. And then that gives me the average atomic mass. So now I'm just kind of rearranging and solving for x. So all I have to do here is collect like terms and then distribute. And so I've kind of done that here. X times 1 is 6.19 plus 1 lot of 108.90 minus x lots of 108.90. So that gives me that first term, collecting the like terms, and that guy there. And so now I can solve for x. I've just got to subtract 108.90 from both sides and then divide by the multiplier of x. So when I do that, I get what x is. And remember that x is the fraction of 107. So it's 51.5% silver 107. My guess was 52%. Pretty good for a guess, right? And so then I want to calculate the fraction of the heavier isotope, and the fraction of the heavier isotope is just 1 minus x, so 1 minus 0.515, that gives me 0.485, and so that ends up being 48.5% of the heavier isotope. Not bad, because my guess was 42%. So I was pretty good at guessing within 0.5%. I might have seen this problem before. Okay, so this is a really, really common Chemistry 161 problem involving average atomic mass that you probably haven't seen in Chemistry 139. Okay, so that ends this section on atomic structure and symbolism. Largely, we're just focusing on how we get the numbers that appear within a periodic table entry for an element. Keep in mind, this guy here is your atomic number. This one here is your average atomic mass that is weighted for the to take into account the natural abundance of the isotopes. The bit in the middle there is just what we call the symbol for your element. It always starts with an uppercase character. If there is a second character, it's lowercase. Okay, hope the video was helpful. Good luck with everything.